An illustrated program shows a picture of its code and data as it executes. Watching an illustration is one way that many people can get an intuitive feeling for how that program executes. Traditionally, programs have been illustrated using a combination of specialized programming languages and specialized programming techniques. In our research at the University of Washington, we have combined a compiler, an interpreter, a type inferencer, and a data illustrator into a tool that automatically generates illustrations for simple Pascal programs. Our system, called uwpi, has been used to illustrate classical array sorting and searching algorithms, as well as several graph algorithms.
For the first demonstration, uwpi has compiled a small program that first reads numbers into an array and then sorts the array using a selection sort. We initially see a window controlling uwpi, several banner and control windows, and an empty window that will eventually be filled with data. When execution starts, we see the source program appear in a window and see that the highlighted statement is the one being executed. We are now sorting the array, which is prominently displayed in the data window. The indices appear as labeled arrows pointing into the array. Some variables could not be placed near the array, so they appear in the left margin. As variables are read or written, they are momentarily highlighted, and all variables change in some way when written. This illustration went by far too quickly, so let's slow the execution down to a more leisurely pace by pushing the Go Slow button and rerun the program. As the program runs, observe that J and I scan the array from left to right, and that J is always greater than I. All the elements to the left of I are smaller than those to the right, and these elements are in sorted order. Min points to the smallest element between I and J. This does indeed look like selection sort. But how did uwpi know how to display the sort? During its analysis phase, uwpi discovers that aside from swaps, elements of the array A are only used in comparisons, so all uwpi can say about A is that it is an array of magnitudes. Since A is the most complex variable, and it is a parameter to the sort routine, it is selected as the backdrop. The variables I, J, and min only index the array A and are drawn as arrows pointing into A. Because these indices are controlled by two loops, each from 1 to n, the only elements in the array that are of interest are those from 1 to n. The other variables n and t do not fit a pattern that uwpi knows, and so they are simply displayed in decimal near the backdrop. During its execution phase, when uwpi enters the procedure, it draws the backdrop A by scaling each element to fit in the space allotted. Reads and writes to the variables are watched as the procedure executes, and the corresponding parts of the display are highlighted or changed as needed. The kind of analysis that uwpi did for the selection sort is relatively insensitive to the order of execution, the names of the variables, and the number of variables. Since most array sorting algorithms compare and swap elements of an array inside of two nested loops, most sorting algorithms will be illustrated in the same manner. For example, bubble sort and insertion sort look much the same, as we can now see. For bubble sort, the swapping of adjacent elements is apparent as the smallest data item bubbles to the left. Insertion sort looks very similar.
Okay, that's it. That's it.
Quicksort is a little more complex, since the array is partitioned into several pieces. Each partition is marked by two indices with the third index pointing to the pivot. The indices are kept on some kind of stack. We have now compiled a non-recursive version of Quicksort. The indices describing the partitions are stored in arrays LB stack and UB stack and indexed by a stack pointer SP. Just as with the other sorting algorithms, the array A that is being sorted forms the primary backdrop. The elements LB stack and UB stack are stored on a second backdrop and point into the array A. uwpi distributed the three arrays onto two backdrops by analyzing the index sets. A is indexed from 1 to n. uwpi could not refine the index range for LB stack and UB stack since the operations on SP do not follow a pattern uwpi understands. Consequently, uwpi retained the declared range of 1 to 20 for both arrays, but since they both have the same index set, they can be merged into the same backdrop. The display is getting a little cluttered. uwpi displays the current values of all of the variables even though some of them will not be used again. For example, values to the right on LB stack and UB stack are still displayed, even though they have no further use. uwpi cannot determine that LB stack and UB stack are instances of stacks, which would follow a slightly different display protocol from ordinary arrays. By comparison, we are now illustrating a recursive version of Quicksort. Normally, uwpi displays all variables that belong to active procedures. However, when executing recursive procedures, uwpi does not display variables that are dead across recursive calls. Local variables that are live across recursive calls are displayed in a stack. Not surprisingly, the end result for recursive quicksort looks like iterative quicksort. We've pretty much exhausted the classical sorting algorithms, so let's turn our attention to graph searching algorithms, which are more complicated. A depth-first search of a directed graph starts at the root and descends all the way to a leaf before backing up. In order to back up, it must keep track of the next node to visit, which can be placed onto a stack. Further, it must mark each node when it is visited to avoid a later visit. When given a direct Pascal implementation of this algorithm, uwpi produces a natural illustration showing graphs and pointers. The programmer used a matrix of integers to encode the edges into the array A. uwpi inferred that A holds booleans, since the values are assigned or compared with two different values which happen to be 0 and 1. It also inferred that the array was a square array. Normally, a rectangular matrix of arbitrary numbers represents loosely structured values. However, a square array of booleans is one way to map values in the range 1 to n onto that same range. This relationship is most commonly drawn as a directed graph. In effect, the inferencer raised the level of the declarations in the program, converting a simple data type and some operations into an instance of an abstract data type. The normal methods for use, range, and backdrop inferencing glue all of the pieces together into a consistent whole. The stack pointers are distributed throughout the graph, and the marks appear on each node. Breadth-first search is like depth-first search, except it uses a queue instead of a stack. A similar analysis produces a similar illustration.
Wait a minute, this doesn't look right. There's a problem here. Not every node is marked, and the queue doesn't thread through all the nodes. There seems to be a bug someplace in the program. Let's run the program again and try and see if we can figure out what's going on. We start off and we advance down. We're clearing off the nodes in preparation for marking them. We advance across. The queue is built up. Oh, there, the queue got clobbered accidentally. Well, Let's run the program again, and what we'll do this time is we'll stop when we are ready to make a traversal across one of the edges in the program. Let's rerun the program and place an execute breakpoint so that when we traverse an edge for the first time, we will stop execution. There, we've stopped execution. We're now assigning the mark on the node Y, which we're visiting. And things look fine. Let us single step the program forward and see if we can pinpoint more closely where Q is being clobbered. We'll continue from the execute breakpoint, hit it again, and we've come to a place where Q indeed has been clobbered. It's gone from head down to tail. So why don't we rerun the program, and this time we'll place a write breakpoint on Q so that execution will stop whenever Q is written. Here we go again. We have a write breakpoint on Q. Well, this is uninteresting. Let's continue execution here. Place an execute breakpoint down on mark of Y gets assigned 0. Place a write breakpoint here so that when Q is modified, and then we'll stop the program every time that Q is modified, and we'll stop. We're inside the loop. We've traversed an edge. Actually, we're down here. We've assigned Q of tail gets assigned Y, and it would appear that the value of tail is being set incorrectly. So we'll rerun the program once again, and this time we'll put an write breakpoint on tail. So when tail is modified, we can see where this is happening. This is not too interesting. We're outside the main loop. We're setting up the Q for the initial element, which is the root element. This seems to be fine. Now we're inside the loop. Oh, we're inside the loop. The Q is empty because head is nil. We're setting up a Q of length 1. And at this point, both head and tail should be pointing to the single element in the Q, but head is assigned to Y and tail is assigned to X. There seems to be the problem. Let's bring up an editor and change that assignment from tail gets X to be tail gets assigned Y. And we'll rerun the program, this time at full speed, to see if the end result does indeed mark all the nodes in the graph. Initialization here, and now the Q is traversing. We are indeed visiting all the nodes in the graph. We're almost finished. All the nodes have been written. This seems to be much better. Let's rerun breadth-first search on a different graph and see if we traverse all of the edges and mark all of the nodes. Initialization, clearing off the marks, traversing across the graph. We seem to be fine so far. Seem to be coming down to there. Yes, here we go. Cross. This seems to be much better. Program illustration has helped us find this bug in our program very quickly.
uwpi can also illustrate some tree algorithms. We'll start an illustration of a program that counts the number of times each element occurs in an array. The program uses an ordered search tree to build the counts. uwpi is implemented in Common Lisp and uses the X display system. You have been watching it execute on a dedicated 10-MIP RISC workstation. The version you have seen is the second prototype, and it was implemented in about 4 months of work. uwpi is built from about 600 Lisp functions. It contains a complete compiler, data flow analyzer, interpreter, unparser, and breakpoint facility for a simple subset of Pascal. The hardest part of uwpi was generating nice-looking graphics. Parts of the inferencer are done in an ad hoc manner. The next prototype should use information derived by using a formal data flow analyzer. The internal connections between the various displays, the interpreter, and the debugger are also somewhat ad hoc and could be improved by using constraint language programming techniques. A cleaner internal design would let us implement a more general data breakpoint facility. We would like to follow the rule, if you can see it, you can put a breakpoint on it, whether it is in the code window or the data window. As we have seen, uwpi knows about arrays, relations encoding directed graphs, pointers, indices, magnitudes, booleans, and integers. It can do a reasonable job combining instances of these data types. It cannot make inferences outside of this rule base, so programs that do not use these data types or idiomatic operations in the stylized ways that uwpi expects will be illustrated at a very low level. However, the rule base can be extended with specifications for different data types and the graphic system extended to generate nice illustrations. Despite the small number of constructs in the rule base, uwpi can automatically generate surprisingly good illustrations for most of the classical algorithms taught in a first semester course. The analysis done by uwpi on vanilla Pascal programs means that a programmer can create a program and quickly get graphical feedback on the relations between code and data, and thus gain an intuitive understanding of how the program works.